Hi, I'm going to be showing you how to do some inelastic and elastic collisions calculations. So some important points are, well, one, momentum is always conserved. So the amount of momentum in a closed system will always remain constant. This is because of Newton's third law. So every action has an equal and opposite reaction. So if I apply a force to something, i.e. I change its momentum, it equally changes my momentum by applying a force back. So just remember that momentum is always conserved. And another key point is that momentum is a vector. So remembering negatives is very, very, very important because otherwise it will completely throw off your calculations. Some important equations are momentum is equal to mass times velocity, and force is equal to change in momentum over time, or alternatively, impulse, which is force times time, is equal to change in momentum. Another important equation for inelastic collisions is kinetic energy is equal to half mv squared. So how to do the calculations? First, you should read the question and really, really take some time to read it because some very small changes in wording can change what it means and really completely throw off all your calculations. So just take some time to read it and understand what it's saying. Next, drawing a diagram is very helpful. So a before and after diagram of the collision. This would be a before diagram. So we have the mass of the first object with some speed u traveling to collide with the second object with mass m2. So we'll look at the momentum before, and we've got to remember the momentum before is equal to the momentum afterwards. So as momentum is mass times velocity, the momentum of this object is m1 u1, oops, and the momentum of this object is m2 u2, I suppose, but as it has no momentum, as it has no velocity, its momentum is zero. Oops. So the momentum in this system before is m1 u1. Now, normally you'd be given numbers for these sorts of things, so you can solve these algebraically. Now, we can look at the after diagram. So generally, there are two cases. The objects collide, and both go off in at different velocities. So here we have m1 v1 and m2 v2, I should say. And the other case is they collide and stick together, in which case they travel with combined mass at a separate velocity. So we know that momentum before has to be equal to momentum after. So let's calculate the momentum after. In the first case, it's m1 times v1 plus m2 v2. Now, in lots of cases, you're going to have to consider whether this v or this v is negative, in which case it can be written as negative or facing the opposite direction. And you definitely have to include that in your calculations. So just draw a diagram and consider whether it's going in the same direction or a different direction as before. And define one of those directions as negative because velocity is a vector. In the second case, it's traveling as a single object. So the masses are combined. So we say that the mass is m1 plus m2 plus this velocity v1. So that would be the momentum after. Now the solution to this would be so in the first case, m1 u1 equals m1 v1 plus m2 v2. And now usually you'll be given numbers for these, and so with some simple algebraic rearranging, you can get the things that you'd need. And in case 2, it would be m1 u1 equals m1 plus m2 v1. And of course, in the same way, you'd be given numbers and you just have to work out one of these. We'll do some calculations later on. Elastic collisions are largely the same thing. Momentum is still conserved, as it always is in a closed system. However, energy is also conserved. In these collisions, energy is likely not conserved. If I hit my table, uh, energy is lost through sound, which you probably just heard, a bit of heat, and that's all dissipated. However, in elastic collisions, we assume that no energy is lost, and so all energy remains as kinetic energy, or useful kinetic energy, because you could also say that sound is kinetic energy. So a very important equation here is kinetic energy equals half mv squared. So the momentum before of this, we should calculate as m1 u1 as before, and this has no velocity, so it's the same. And the energy here, we have to say is half, so I'm going to write 0.5, if you could see that, m1, and then u1 squared. And this u1 is the thing that's squared, not the entire mass and 0.5, because that would, well, that's a different equation altogether. So 0.5 m2 times 0 squared, which we know will be 0, so therefore we can just remove this. And as before, you'll get numbers with these things so you can work these out. Now for after, you'll be given mass, velocity, mass, and velocity. And generally, if m2 is very large, you shouldn't draw a diagram like this. You should do something, akin to a big wall. M1 goes in and comes out with its negative velocity, like that one time Nick threw a dinosaur at the wall and it just came bouncing right back. So the momentum after here, but we're assuming that these are relatively similar masses. The momentum after will be m1 v1 plus m2 v2, just as if it were an inelastic collision, and we have to resolve the energy, and it will be 0.5. I'm going to move this down, and it will be 0.5 times n1 times v1 squared plus m2, pardon me, 0.5 times m2 times v2 squared. Now together you can equate the momentum and you can equate the different energies, and because you know no energy is lost, and so they should be the same, and this will give you a pair of simultaneous equations to solve. This likely will get very algebraic, but it should give you the correct answer, and we can do an example of that later on. So in some cases, you'll be asked to assess whether a collision is elastic. This might sound a bit difficult, but really you just need to calculate the energy before and the energy after, which is really just the same as what we've done here, except you don't equate them, you just look at them and say, okay, the energy after is either the same or less than before. If the energy after is less, then it's an inelastic collision because energy has been lost. If it's the same, then it's elastic because no energy has been lost. Really quite simple. So let's do some examples. So the diagram shows an experiment with two trolleys. The first trolley A has mass 0.95 kilograms and B has 1.40 kilograms. They suddenly explode with B rocketing away at 1.20 meters per second and A traveling away with another velocity in the opposite direction. So here, this is an inelastic collision. It said that before in the question, but I didn't include it in the screen cap. So we only know that momentum must be conserved. So Looking at the diagram, before there is no momentum. The trolleys are stationary and so have velocity 0, and therefore we know that there is no momentum. The momentum after, however, is 1.2 times 1.4 plus 0.95 times this v that we have to find. Oopsie daisies. This is because B has velocity 1.20 meters per second and mass 1.4. The mass hasn't changed. And so we know the momentum is P equals mv. And we do the same with A. Now we know the momentum before has to be equal to the momentum after. So 0 equals 1.2 times 1.4 plus 0.95 times v. And therefore we can just do some simple algebra on this, and we get v times 0.95 equals 1.2 times 1.4. However, this will be negative because we've just subtracted this onto the other side. And then we can say v equals, and then if we divide through by negative 0.95, we get 1.2 times 1.4 on negative 0.95. Now for the elastic calculations. So an object of mass m1 equals 2 kilograms, moving with velocity v1 equals 12 meters per second, collides head-on with a stationary object whose mass is m2 equals 6 kilograms. Given that the collision is elastic, what are the final velocities of the two objects? Neglect friction. So we know this is an elastic collision, given that the collision is elastic. And we know that these masses are not so different as to cause the first mass just to bounce right off, which would happen, as you remember, when Nick threw his dinosaur at the wall, it just came right back. So the momentum before the collision, P equals mv, we must consider. Pardon me. Now, when calculating elastic collisions, much the same as calculating inelastic collisions, you just have to calculate the momentum, and then before and after, and then do the same with energy. It's just the same thing with a different formula. Apologies for my stiffing. So, 2 times 12 meters per second is the momentum, because this is stationary at the start. So we get 24 kilogram meters per second. I assume you're fine with that. And the energy before is 1/2 of 2 kilograms times 12 meters per second squared, as is half mv squared. And this amounts to 0 as it's being multiplied by 0 squared. And this comes out at 144 joules. Now, the momentum after, much the same. We say that the two particles move away from each other with different velocities v and u. So 2 kilograms times v plus 6 kilograms times u is the momentum afterwards. And following the same trend, the energy afterwards is 0.5 times 2 kilograms times v squared, as by the formula, plus 0.5, which is a half, times 6 kilograms times u squared. Now, that was the easy bit. Just a small bit of algebra and we'll be through. So, we can equate the momentums and say that 24 equals 2 times v plus 6 times u, because we know that the momentum before is equal to the momentum afterwards. We can minus 6u from both sides, and we get 2v equals 24 minus 6u. We can divide through by 2 and say that v equals 12 minus 3u. Now, we want to be able to plug this, something from this into this. So there's a v squared in this part of the equation, in the energy part. So I'm going to look for a v squared. Before we do that, we can take a look at this. So because we know it's elastic, we know that the energy after is equal to the energy before. So 144, as calculated, is equal to 1/2 times 2, which is 1 v squared, plus 1/2 times 3 times 6, which is 3u squared. And as I said, I want to be able to put this into here. So to do that, I'm going to square the v. And so I square both sides of this equation, and I get v squared is equal to 144 minus 72u plus 9u squared. So I'll put that in place of the v squared here, and I get 144 equals 3u squared plus 144 minus 72u plus 9 squared by just putting this into here. So 144 minus 144 equals 12u squared minus 72. And then factorizing that, we get u is equal to 6 and u is equal to 0. The beauty of this being that if we look here, we have two states, one where this u is equal to 0, and one where this u is equal to something else. And so we know that after the collision, its velocity is 6. Now we can work out v from that. Going back to one of our initial equations, we say that 12 minus 3u is equal to v. We know that u is 6, or u is 0. So we say v minus 3u, 12 minus 3 equals v. V equals 12 minus 3 times 6, which is 18. So 12 minus 18 is minus 6. So v is equal to minus 6, u is equal to 6. Or alternatively, we can say that v is equal to 12 minus 3 times 0. So v is equal to 12, as was before the collision. And that's how you do these inelastic collisions.